All right. Good afternoon. Hello, everyone. All right. So we are 3 weeks in. So we have 2 more weeks of stuff, and then it'll be the week of our exam, our first test. So we're starting forces now. So just to remind you all, last week was 2D kinematics. We finished that up. So your quiz for that's due this. And again, quiz the 5 problems or whatever thing. So make sure you're working on 2D kinematics, and then this week and next week is all forces. All forces, we'll use kinematic stuff here and there throughout it, but it's kind of like its own topic in of itself. If you had to break up the test, it's kinematics is half of it, forces is the other half. That's test 1. So this first class is going to be on Newton's laws, which you've probably learned, like you've probably heard these at some point in some science class. But the vast majority of you all, there will be something in here that you won't expect. These laws are really, really basic laws, like very simple descriptions. They're called laws because they're based on observations of reality. They don't say why things do what they do. They just say this is how the world works. So like this, the first one is an object in motion stays in motion, an object rest stays at rest until a force acts on it. That's just like observation of reality. It doesn't say why things do what they do. It just says things do this. And that's why they're laws versus theories. They're just basically a description of reality, not explaining why it is. So, they are, again, there will be some, this is one of my favorite things to kind of go through because they're such simple ideas, but they're going to have effects that you might not realize. Effects all around, like, explain so many things around you that, like, you know what's going to happen, but this will help you kind of have, like, a better understanding of it and, explain some things that you thought might have been due to other things, whatever. I like this a lot. It's fun to go through. So there's like minimal math in this. It's mainly ideas. And these ideas are fairly important to understanding, predicting, all that kind of jazz. So today we'll actually probably get through pretty much this entire thing, almost all of it, if not all of it. And then next class and the ones moving forward, we'll start to get into equations and math and things like that and applying it. So yeah, this is a concept-heavy day today. We're going to define what a force is, and then relationship between force, mass, and acceleration, and free body diagrams, and all that good stuff. So the bread and butter of forces, what the heck are they? All that good stuff. All right. Do I want to open a question for this? How do you cause an object to accelerate? All right, let's just, make this simple. There's an eraser. If I want to accelerate it, tell me what to do. Throw it. Great. That works. That's, so that's the name of the game today. It's like, how do you make stuff, the long and short of it's going to be, how do you make something accelerate? The phrase everyone uses, a force. I've heard that word. But what is a force? And we're just going to use a really basic definition. A push or pull. You push it. Now, how you push it or how you pull it, that's where things vary. And what if there's a bunch of things pushing and pulling on it? And what if instead this was a car instead of an eraser? Like all the nitty gritty we'll get into, but that's basically the principle. How do things accelerate? This guy invented something called a force, and we'll talk about it. Again. It's going to be something that fundamentally it's just push or pull. That's the end of the day. The long and short is push or pull, but we're going to build on this. We'll look at simple circumstances where one thing's pushing or pulling on it, and then there'll be many things. There'll be vectors and components and all this good stuff. So we did things that studied an object motion. Forces are the reason for the motion. We've been doing problems where things accelerated. The question is, why did they accelerate? This whole section is, why do things accelerate? Determining that acceleration based on the forces out there. So that's kind of the difference between these 2 weeks. Studied how things move. Now we're going to talk about how do you get them to move in the first place. Which fundamentally is very simple, but again, anything simple can become complex pretty quickly. All these slides, a lot of stuff today, I'm not going to ask you these questions on a test. I'm not going to say what's the definition of a force or none of these kind of vocab-y things I'm going to test you on, but I mention them because they're important for us to just have the jargon down. There is a direction. If I push this thing to the right, it's vastly different than pushing it to the left. Remember, the definition of a vector is if the direction matters, it's a vector. Direction magnitude, so we're going to have to deal with that. And this last one is interesting. Physical contact is not required. In fact, every single force, fundamentally, there is no physical contact. I mean, yeah, so we'll talk about this in a bit, but fundamentally, nothing is truly touching. What does it mean for things to touch? We'll chat about that very, very briefly. Forces, push or pull. Really, really straightforward definition of it. That's the one we're going to use. The next, again, a lot of these first slides, they're just kind of fun knowledge, especially this next one. This next one, I'm not going to test you on at all. There is all the pushes and pulls in the entire universe. We categorize them into why something is causing that, and different reasons for those forces. And there is 4 categories that every single push or pull in the universe will go into one of these 4 categories. Anytime you all have seen something get faster or slower, the reason behind it can be categorized in one of these 4 categories. And 99% of the pushes or pulls that you've seen in your, let's just say 95%, depending on your perspective, fall into one of these. And it's not probably the one, well, we'll see if it's the one you expect. So there they are, 4 forces: gravitational, electromagnetic. Again, I'm not going to test you on this, so don't worry about this as far as like needing to memorize it. But it's fun to know. Gravitational force, electromagnetic force, strong force, and weak force. Every single push or pull can be categorized into one of these. And basically the way these were discovered was they saw push or pull. So gravity, is easy. Gravity is like, let's start there. Okay, I'm holding an eraser. If I let it go, what's it going to do? Oh, it got pulled by something. Oh man, I wonder what pulled it. And they came up with gravity, Isaac Newton. Now that's a much easier thing said than done, but great, that's one pull. It got pulled down by gravity. And then we'll actually cover this equation after test 1 sometime. We'll go through the equation to calculate this between any 2 objects, things that have mass. Very exciting, great stuff. Great, that one's straightforward. That does not explain most interactions. When you look around this room, most things that are moving aren't being pulled by gravity. So then it's okay, what explain? So right now, for example, the eraser. We said, great, it should be pulled downward. But it's not falling right now. It's sitting on a table. So then the next question is, something must be opposing that. Something must be pushing. Okay, great, the table's pushing up on it. Why? That's kind of this is how anything is discovered. People look at something and say, my current knowledge doesn't explain this. Let me try to understand. Maybe it's something else. So they look at this and they say, gravity pulls things towards each other, but there's something pushing upwards. I mean, if gravity pulls it down, it's not falling down. What's up with that? And this is eventually they learned that protons, electrons, neutrons. Physics 2 is the electromagnetic force. All of physics 2 basically is that force. The electromagnetic force explains every single, other than you all being pulled into your seats right now, every other thing you're experiencing is electromagnetic force. When I threw that eraser across the room, electromagnetic force. When you're sitting on your chair and the chair's pushing up on you, electromagnetic force. The reason your clothes stay on you, electromagnetic force. Friction, electromagnetic force. Rope pulling something, electromagnetic force. And you're like, okay, what does that mean? Everything's made of protons, neutrons, and electrons. You'll learn in physics 2 that, you already know probably a good amount of this, but things are made of atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons chill in the middle of the atom. And then you got this sweet electron cloud on the outside of it. Electron cloud means you can't exactly figure out where they are. And you got another atom, and they're coming in close. And they get near each other, and it turns out that the electrons repel each other. And so nothing is truly touching. The electrons aren't literally physically bouncing off each other. But when they get close, you can almost think of it like magnets. They're not magnets. Well, electrons are technically tiny little magnets, but that's not the reason they repel. They have charge, and you'll find in physics 2 there's an electromagnetic force. They repel each other. Coulomb's law, future things. And so nothing is truly touching. Gravity you all experience gravity even if you're in the air. Even if you're not like touching the earth, you get pulled down by the earth. You're not touching the earth and yet it pulls you. The electromagnetic force, same thing. Two electrons are next to each other. They're not touching, but they still repel each other. So yeah, when you touch something, the reason that you eventually stop being able to eventually feel that repulsion is they just get close enough. You got to get really close for this force to kind of take place. These electrons got to get real close before they start. You'll learn it's 1/r squared and all that jazz. Anyway, explains most things. Most pushes or pulls is this one. These last two, the statements I'm about to tell you are probably the only time you'll hear these ever mentioned in any class moving forward. So I mention them because I had one teacher mention these forces that I remember, and the amount that he said is the amount I know. It's literally a handful of sentences. So I will pass on my precious knowledge to you, and if you too will know a handful of sentences about these. The strong force, so back to the whole electromagnetic force, remember, the way we discover these is we say there's something that one of these doesn't explain. So I just told you that opposites attract and like charges repel. You got a positive and a negative, they're going to attract to each other. You got two positives, they're going to repel from each other. That's physics 2. You'll learn all that, but you probably learned it before. Well, inside an atom, inside the nucleus, is a bunch of positive charges, all smushed together. They shouldn't be smushed together. Positives should repel each other. So it can't, it's not doing what we expect. So they said there must be some other force holding these protons together. So they said it's a new force. It's a strong force. And the amount that I'm about to tell you is the amount I know. You've been told that protons, electrons, and neutrons are the smallest particles. That is not true. There's smaller particles than those. Protons, neutrons, and electrons are made of smaller particles. And, how far down does that go? I don't know. But particles are made of particles it just keeps going on. I have no idea how far down we've reached at this point. But protons are made of quarks. I think 2 up quarks and 1 down quark or something like that. And these quarks exchange gluons, and that holds them together. That is literally the extent of my knowledge. Sounds made up, but that's the amount of my knowledge. Yeah, so that's the strong force. If that's not satisfying to you, Google more things because that's the amount I know. For me to learn more about this, you kind of have to take a nuclear class or things like that, or I don't even know where they cover this, to be honest. I have no idea. I've never taken a class on it. But there you go. Quarks exchange gluons, and protons are made of quarks. Your life is the same as before. But it's interesting. Again, you'll never hear someone mention this again, maybe. If you do, I'd be surprised. If you've heard that mentioned before, let me know. My quantum teacher mentioned it one time in 2 sentences, and that's fine. The weak force. So again, we look at all these scenarios, any push or pull. At some point, there is some atoms that have a lot of protons and neutrons in them, and they just fall apart. Half-life. At some point, atoms randomly fall apart, and it's that doesn't match the other things we know. According to the strong force, they're supposed to stay together, but at some point they fall apart. The weak force explains radiation. That's the extent of I know about the weak force. I don't know why things do that. You can say they become unstable, but then the question, why do they become unstable? The weak force, I don't know. That's the most I know. As you get through this list, especially these last 2, I don't really know much. But now you know a little bit more than you did before, and I'm never going to test you on this, but, you can tell other people, and they'll give you the same look you're giving me. Forces. Every single push or pull goes into one of these 4 things. They're independent of each other, so that's an interesting little fact. One of the things, they made a whole movie with this name, I think Grand Unifying Theory. Isn't there something about Stephen Hawking unifying theory? I don't know. I feel like there's some movie with this name. There's this idea of a grand unifying theorem that will combine all these together and we'll all realize they're all one thing. That's theoretical right now. It hasn't been proven. There's, as far as we're aware, these are separate from each other. And they're independent. And at some point, someone discovers some thread connecting them all that won the Nobel Prize. It'll be a beautiful moment. But at this time, we don't know what that we don't even, there's a theory, there's a hypothesis that they could be all connected, but And really, one of these comes down to, it's really interesting. We'll learn in this class the equation for gravity is G m1 m2 over r squared. Again, don't worry about this for now. Mass, distance, the G is just a number. What's really weird is the electric force is K Q1 Q2 over r squared. So even though they're completely independent of each other, the equations look the same. So it makes people like, huh, that's weird. So that's where some of these ideas, like maybe there's something unifying these. I don't even know the equations for the other one. So, all right, great. This slide, whatever, contact forces, field forces. In our class, we will consider things touching, but fundamentally they don't. All right, fantastic. This guy, what a guy. Isaac Newton is just one of those people. You'll meet people in life where you're just like, man, that guy, that gal, that whoever, they're able to just like figure out things that I'm like, how are they that? We often use the word intelligent, but intelligence is in a bunch of different domains. We just have these people like, how do these people do this? Like, how do they come up with these things? How does this person know this much information? How is this person this clever? Whatever, insert the word. This is one of those people that you just look at and like, how was someone this capable? Like, how did someone discover this many things on their own? This guy discovered the laws for forces, which again are going to sound simple, but no one else had come up with them before. And they explain things you're not going to explain. They explain things in space and things that we hadn't gone to space yet and all that jazz. He came up with that. He discovered the equation for the force of gravity, that 1 over r squared. Super clever, looking at the moon, doing a lot of clever things. He discovered how light behaves and how it splits up into things and refracts. He was one of 2 people who independently discovered calculus, like invented calculus. Him and someone else did it independently. He just did so many things. You're just like, it's nuts. So one of those people, genius, you're just like, their brain, how does it work this way? Wild. There's people like this. I've met students like this where it's just like, your brain works different than mine. It's very impressive. He's one of those cases. Very interesting individual. He's the one that came up with it. It's always good to credit it. The units for force are named after him. That's going to be a common theme, that whenever something gets discovered, the unit gets named after them. So newtons, that's the unit for force. When we get to energy, it'll be joules, named after a guy with joules. When you get to physics 2, coulombs are for charge, named after a guy with the last name Coulomb. Resistance is in ohms, named after a guy with ohms, so on and so forth. If you ever see a unit like, that's a weird name, it's probably named after someone. That's why. How it goes. Meters, kilograms, I don't think those are named after someone, but the fancier ones are. Okay. Into Newton's laws. Before I introduce each of these laws, or maybe even after I introduce them, there's going to be a lot of these kind of questions today. And some of these are going to be obvious, and some of them you're going to be surprised about. Even though the principles, the reason for the answers is very straightforward. So using these very straightforward rules, we're going to be able to explain things that you might not expect. We'll go counterintuitive. So I find this very entertaining. So do not look at these questions and say, is this a trick question? I want you to just look at these questions and say, what do you think is going to happen based on what you know? Don't try to guess if they're trick questions. None of these are trying to be trick questions. So use what you've experienced in reality, think through the logic, and come up with an answer. If you fire a bullet in space, what will eventually happen to the bullet? Will it slow down and come to a stop? Will it get faster and faster? Will it keep traveling until it hits something? Every single question today only has one right answer. There is no questions I'm going to give you that have more than one right answer. So, make certain you're chatting with the people around you. If you have different answers, one of you is wrong or both of you is wrong. Mm-hmm. So as long as your grade is showing up in top hat, you're good. There's about 10 to 20% of people whose grades aren't syncing to Canvas, and I just have to do those manually. I found the reason why. There's no way around it. But as long as you have a score in Top Hat,
where do I find that?
Should be somewhere. I'm not sure what it's going to look like on your end, but you should be able to see your points and things like that in Top Hat. Great. Yeah. Yeah. So that's as long as it's showing up in Gradebook and as long as it's showing up in Top Hat, you're good. Yeah. Some of them aren't syncing over, and that's a thing. It has to do with some email stuff, and there's not an easy solution to it per se. It's not like I just tell people use this email, because which email varies, and so it's just getting something out of it.
Okay, well, I need to email you.
No. As long as your grades are in there, I'll be able to pump them over. Yeah. All right. 10 more seconds. And 5, 4, 3, 2, 1. All right. So again, every question we're going to kind of do today, we're going to try to connect it to an experience you've already had, and then if it's a new scenario, none of you have been in space. That's just not a thing. Maybe one day. But for now, none of you have been in space, so there is some new stuff. Great. I roll a ball. Will it roll forever and ever and ever? No, I mean, assuming it doesn't roll off the table, eventually things stop. You take your foot off the gas, things stop. Why? Why is it when you take your foot off the gas, your car eventually stops? Friction, air resistance. Great. We're in space. Does any of that exist? Nah. So you get rid of that, and the question is, it shouldn't stop. If that's the reason it stops, and you get rid of it, it should no longer stop. And that's the answer. It will go forever and ever and ever and ever and ever at a constant velocity. It will not get faster. It will not get slower. It will not change direction. It will keep going forever and ever and ever and ever and ever and ever and ever until something affects it. And that is Newton's first law. Newton's first law says an object at rest remains at rest. An object in motion remains in motion until an external force acts on it. Until some force acts on it externally. It can't be something inside the system. If there was like a little rabbit in here and it was running in a circle, that would make the thing spin, but it's not going to make it change direction. So it has to be something outside of it affecting it. If you are in space, well, there is a caveat to this. If you're in space, no amount of wiggling around is going to make you move in any direction. But we are going to find if you throw something, that will make you start moving the opposite direction, and we'll see why that is. So there's a little caveat here. But yeah, my definition, things keep doing what they're doing until acted on by a force. They will keep going in a straight line at a constant velocity until something affects them, gravity, or they hit something, or anything like that. Inertia is a word that we use to describe inertia is a funny word to describe, but I kind of view the word inertia as how hard it is to change what it's doing. And there's kind of two ways of this. Either it's got a lot of mass. I mean, you've experienced this. Think of like things that are hard to stop. It's really hard to stop a big object that's moving. Car. Doesn't matter if that car is moving fast or slow. It's pretty hard to stop a car that's moving. It's also hard to stop things going really, 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 really quickly. Good luck stopping a bullet. Like, they go really fast. So those both have high inertia, mass, velocity. Fantastic. Okay. So that first question, fantastic. This next question, the wording is not ideal, but it's the best I could come up with when I was doing this question this morning, because this is going to have some interesting connections to things that you've experienced. So this is the one I picked. You are standing in a bus as the bus makes a sharp turn to the right. Standing in a bus makes a sharp turn to the right. Right as the bus starts to turn, you jump into the air so that you're no longer touching the bus. When you're in that air, as the bus is turning, what forces do you experience? Are those forces, is there a force down and to the right? Is there only a force downwards? Is there a force down to the left? Basically, the question is, what direction are you being pushed or pulled when you're in the air? Remember, a force is just a push or a pull. All right, we'll go like 20 more seconds. All right, 5 more seconds. So 5, 4, 3, 2, 1. All right, so we get to do a little bit of foreshadowing. So something we're going to do in this class is called free body diagrams, where you draw the object and you draw all the forces acting on it. That's how we're going to solve these problems eventually when we get to numerical. Every single object is going to look like a square. That's a person, that's a car, that's a whatever. Look, if you really want to, you could draw the person, but that takes forever. You know what's easy? A square. Or if you really want, a circle. I don't really care what your object looks like, but you know, that's nice and easy to draw. That's my person. You can tell because I said so. Then you draw the forces. When they're in the air, what's the obvious one acting on people? We've talked about this for the past couple weeks. When something's in the air, what's pulling them down? Great. Notice that all these, except the last one, had gravity. So this is something, eventually, we'll kind of get to the nomenclature here. Great. You're in the air, gravity's pulling you down. When you're in the air, is there anything else pulling you any direction? Now, there's no strings attached to you. Sure, the bus moved, but there is nothing connecting you to that bus, so that if the bus moves, you're going to move with it. If you're in the air, nothing's going to be pulling you. So there is only a downwards force. And so the reason I asked this question, so good. Get some different answers here, which I appreciate. What I want to try to explain to you all is that when you take a turn, so you all been in a car, you take a sharp turn, you feel like you're getting thrown to the outside of the car. Take a sharp turn, you feel like your body's getting pulled to the right. Nothing is pulling you. Nothing is pulling you. I mean, think through that logic. When you make a turn, what would be pulling you to the right? There's no string attached to you. There's no gravity pulling you to the right. There's what would be pulling you? So then the next question is, why do I feel like I'm getting pulled to the right? That's kind of the purpose of this question. So it's pretty easy to show. So I got a notebook. It's what I found in the room. It's got some low friction, which is nice. So here's you. You're this eraser. The notebook is the car. The car is moving, and you're moving with it. And then the car takes a sharp turn, and you don't stay in the car because of Newton's first law. So this is the reason you experience that pull. It's not that you're getting pulled, it's that the car is leaving you. And if the car doesn't push against you, there's no reason you should turn as well. The only reason you make a turn in a car is because the car has to push against you in some way. Seatbelt, wall of the car, something. Otherwise, Newton's first law says you're going to keep moving in the direction you move. You're going to keep moving forwards. The only reason you're going to turn with that car is if a force acts on you, i.e. seatbelt, the chair, the wall of the car. If you've ever been in like a golf cart or something like that and they take a sharp turn, you will fly out the side of that, not because anything's pulling you out of the car, but because of Newton's first law. You will keep going forwards. Why wouldn't you? Your body doesn't magically know that the thing turned and know I should turn with it, unless something pushes you. So that's one of the interesting consequences of this law that you experience all the time. When you make a turn, nothing is pulling you to the outside of your car. In fact, the opposite is true. The car is keeping you inside. You're actually getting pulled the other way, inwards. If you weren't, you'd fly out the car. Another good example of this is if you all have ever been to the carnival rides, and they have the ride that spins you in a circle really, really, really fast, and you get stuck to the wall, and it feels like you're getting pushed outwards. You're not getting pushed outwards. You just want to keep moving in a straight line. And there's something. So let's just look at the top here. When this thing is making a spinning motion, you're moving. You're not moving at that exact moment. You're moving, in this case, to the left. At the very top of the circle, at that exact moment, you're moving to the left. And so if somehow, some way, a hole opened up in that thing, you'd fly in a straight line to the left. If you left this thing, you're not magically going to keep doing an arc, because why would you? What would keep you in that arc? There's nothing pushing you in that arc. You're going to go in a straight line. Well, so how do I go from this spot on the top to this spot that's a little bit lower? It has to push you down. It has to push against you so that that arrow up there eventually rotates down. That's acceleration. I'm changing the velocity. I'm changing the direction of it. So we'll eventually do circular motion stuff at the end where we'll see this. Because this is my velocity at some point. This is my velocity at some other point. My velocity vector changed. Previously, it was all in the x direction. Now it's a little bit in the y direction. When you turn, so like if I'm walking in this room, I'm walking to the left, my x velocity is negative. When I then turn and walk towards you all, my x velocity is 0 now. It changed. Making a turn is, you're changing your velocity, the components of it. So yeah, interesting consequences of this. This is why seatbelts are super important. When a car comes to a stop, your body doesn't magically know to stop. Something will stop you. You get to decide what's going to stop you. Is it going to be your seatbelt? Is it going to be the steering wheel? Is it going to be the windshield? Is it going to be what's on the other side of the windshield? You will stop. You will fly. You're going to hit something. Is it the seatbelt? So on and so forth. Newton's first law explains why that stuff's important. It's why motorcycles are so dangerous. Your car has a lot more cushiony things in it than the outside world does. The most dangerous thing in a car accident is getting thrown from the vehicle because everything outside your vehicle is really hard. Maybe you're lucky to land on grass, but roads most often don't have that much grass around them. You're going to land on the road or hit some concrete structure or hit another vehicle or, hard things. Hard things hurt. We'll learn why. That's another one of the laws in here. And, your car's got nice things that are much, much softer. Airbags, seatbelts. But yeah, this is the reason motorcycles are more dangerous. You're going to get thrown from a vehicle if you get hit on a motorcycle. Like, it's good luck staying on that thing. Wearing a helmet protects your most important bits, but the rest of you will hit other things. And yeah. So I say that not to say that don't ride a motorcycle, but that is the reason they're more dangerous. Physics says so. All right, so this question kind of relates to that. Why do people get concussions? This one I'll give you all like a minute or so. Again, all connects to Physics 1, but connecting it to a medical context. Why do people get concussions? And try to connect it to Newton's first law, because it explains why. We'll go for like 40 more seconds. All right, 10 seconds left. Don't worry about putting some super thought out thing or anything like that. Though if you have the time to do so, that is nice. But remember, as long as you respond, you'll get the points as far as that's concerned. All right, and we'll close this out in 5, 4, 3, 2, 1. All right, so let's see what people put. Don't worry, there's no names, so you're not going to be, unless people put their name there. Brain impacts inside a skull, force to the brain shakes, contact, force and acceleration, too many forces, you hit something, brain's moving. So yeah, all has to do with the brain, and it's moving, and it hits the skull. The question is, why does it hit the skull? Newton's first law tells us why. You've got someone, there they are, and there's their brain. They are moving. So their brain is moving. And then they hit something, like a wall. Their head is no longer moving, which has its own consequences for the skull. But the brain is still moving and will therefore run into the inside of the skull, and the inside of the skull stops it. And I guess there's like a little bit of fluid in there, which provides some cushioning. And also the brain can just withstand some amount of like getting hit by stuff. But yeah, your brain is effectively running into the inside of your own skull because of Newton's first law. Your brain is moving and then it stops because your head hit something. Otherwise, it would fly through your head, and that's a bigger problem. When you stop, your brain's got to stop. And so there's a limit to what you can experience. I asked Copilot today, and it said about 70 to 120 Gs. And if you're curious what that means your brain can experience, so a G, 7, let's just say something like this, give or take. Everyone's brain is different, so complex. This is acceleration. This is the acceleration your brain can experience without suffering a concussion, roughly, according to, again, fact check me on this. That comes out to, how do you it's 7, let's just take 70. You just multiply it by 9.8. You all know the value of G, multiply it by that. That's going to give you the acceleration that you can experience. That's roughly 700 meters per second squared. So yeah, when you hit something, it will stop. That's the amount of stop. If your acceleration is bigger than that, then it will suffer damage. Give or take. Newton's first law explains why you get it's the same reason you wear a seatbelt. This is the same thing. When you're in a car and it stops, something's got to stop you. Your brain, everything in your body, when you hit something, all the fluids in your body, they're all still moving. This is one of the reasons why if you're experiencing if you're in a roller coaster, or the extreme example is a fighter jet and they experience a bunch of Gs, the blood all pools at one part of their body because the blood is an independent thing that also has to speed up. If you don't give it time to speed up, it's going to all kind of build up on the bottom. If your body is getting pushed upwards, your blood doesn't know to magically move upwards until the body pushes it. And so if you experience 10 Gs, it can't quite keep up. And so the blood then ends up more at the bottom of your body. You need blood at the top of your body, and then you'll black out. All of Newton's first law explains all these things. Such a simple thing and explains so many consequences. So something's slowing down or speeding up, a force is acting on it, guaranteed. If an object is going at a constant speed, that means the force is zero. The net force is zero. Nothing is making it faster or slower. It doesn't mean there's no forces. It just means they're all canceling out. Right now, you all are moving at a constant speed of 0. Gravity is pulling you down, but you're not falling. Your seat is also pushing up on you. So, it doesn't mean there's no forces. It just means they cancel out. No forces, no change in motion, and an object that is turning is experiencing a force because the components are changing. So this is one of those mindset shifts you all have to get into, is that everything is X and Y. Everything has to be split up. And if one of those components is changing, there's an acceleration. If a component of velocity is changing, there's an acceleration. All right. Great. Fantastic. That was just one of the laws. And so many things it explains. So many things. All right. The next one. What's harder to move on Earth? A small car or a big truck? Again, don't be thinking about these and whether or not they're trick questions. Think through your experiences. Think through the reasons and all that jazz. So don't just come up with an answer here. Come up with why you think that is. Because I'm just going to go ahead and tell you the next question is going to be in space. And so you got to think through the logic here. If you understand what's on Earth, why is that? So that when you go to space, does that change things? like 20 more seconds. We'll close this one out in 5, 4, 3, 2, 1. So, if ever you're uncertain on an answer like this, make it more extreme. Instead of a small car and a big truck, make it a baseball and a big truck, I guess. Whatever. I don't know. It's easier to move a baseball than a big truck. Like, woo, I can toss this baseball. I am not going to toss a big truck. Like, that's not happening. So the answer here is, what's hard to move on Earth? The big truck. Matches what you expect. Okay? Now let's go to space. So now the key here, and I even put small in front of it and big truck to make it more clear. Think through the reasons why you made that decision. Why was it easier to move a small thing on Earth versus a big thing? And then think through, okay, in space, does that thing change? And you can use that trick and make it extreme. Replace the car with a baseball. Go like 20 more seconds. And 5, 4, 3, 2, 1. All right, so again, let's take the more extreme example, because you can do this. This is a thing you can do in physics. If you have an idea here, you're like, oh, I'm really not sure, they're similar, make it more extreme. Make the difference more extreme. So let's just pretend like it's a baseball or a big truck. What's harder to throw in space? Speeding up is effectively, if you throw something, you're speeding it up. It's much easier to make a baseball speed up in space than a big truck. If I'm in space, I can't just throw a big truck. Another way to think about that, think of the astronauts on the International Space Station. If they go outside the space station, it's not really easy for them just to push the space station, but they can throw a wrench or something like that. So this is one of those things, and I expected, this is one of those things that, funny enough, the answer is the exact same as the last one. And so the thing that throws people off here is we're so used to gravity and weight and things like that. Let's take another situation. So it's often friction is the thing that we're battling on Earth. Bigger things have more friction, and that's a problem. Let's put something on ice. Let's get rid of friction. So then in that case, we're not really worried about friction. It's really easy for me to push a baseball or something on ice, whereas a really big object, even though there's no friction on ice, effectively, it's really hard to push that thing. Space is the same way. Or if you're underwater and, things are weightless, underwater, things kind of float around. Yeah, if you go in the water and you try to push an entire cruise ship, it ain't going to happen. And the reason for this, this is Newton's second law. It turns out that it doesn't depend upon the weight. It depends upon the mass. And this is a subtle little difference. That's very, very, I say subtle, it's a pretty big difference. Mass is how much stuff something has. Literally the number of protons, electrons, neutrons. Things have more mass when they have more protons, neutrons, and electrons. And you can just think of it it's really hard to move a lot of particles. More mass just means I'm moving a lot of particles. It's harder. Whereas when it's really small, it's less particles. It's like saying it's easier to move 5 marbles than a billion marbles. That's effectively what mass is. So Isaac Newton discovered this, that the force, that's something, the acceleration, the force, they're all related to the mass of an object, not the weight of it, but how much stuff it has. Mass is going to be measured in kilograms in this class. So kilograms is not going to be weight in this class. Just like your chemistry classes and all that, kilograms is mass. It's a measure of how much stuff is in something. Not how much gravity is affecting it, but how much stuff is in it. Literally like how many atoms and things like that. That's what mass is. Not about how much space it takes up. We don't care about that. You could have a giant balloon and it has like no mass. You care about the literal number of like atoms and protons and all that jazz. The base unit for mass is kilograms. The reason for that is I have no idea why. I don't know why it's not grams, but someone decided at some point it's kilograms, and here we are. That is the base unit. Do not use grams in these calculations, otherwise you will get the wrong answer. These equations are calibrated for kilograms. So this equation says, honestly, the second one is the one that's kind of better. It's all about acceleration. How much an object accelerates is actually what's going to happen to it. And you can find that acceleration by taking the force you apply and dividing it by the mass. The unit of force is newtons. But yeah, Newton's second law says F equals ma. F net equals ma. The relationship between force, mass, and acceleration is F equals ma. That's probably one you've seen before. If not, there it is. It's a really nice and simple equation, and it's really going to be the bread and butter of what you're going to be using for the when we actually solve problems. I do want to point out this now. F net means add up all your forces. This little symbol here is a sigma. It's capital sigma in the Greek alphabet. It stands for, so this is sigma. It means add. This means add all the things. Sum them up. So whenever you all see that symbol, you're going to see it in this class. You're going to see it in physics 2. It's our shorthand. It's our math way of writing. Add everything up. Add up all the forces. F net. Net means add them all up. This is the other way we write it. And it turns out if you add them all up, it will equal the mass of the object times its acceleration. Yeah, there's a lot here. It's interesting. At the end of the day, it's just F equals ma. What a simple equation. But there's a lot to kind of take in here. The other big takeaway I want you all to know, and I'm going to keep repeating this. If I tell you I push something with 1,000,000 newtons, that does not tell you what the object's going to do. I say I push an object with 1,000,000 newtons. What's going to happen? You don't actually have a good sense of what's going to happen. Because if I push the earth with 1,000,000 newtons, not much is going to happen. Because the mass of the earth is absolutely massive. And so if I push it with 1,000,000 newtons, who cares? The mass of the earth has 24 zeros. Like, it ain't going to do anything. Whereas if I push a baseball with 1,000,000 newtons, if I divide 1,000,000 by like half a kilogram, this thing is going to accelerate stupid amounts and like this is like way different. So acceleration really gives you a better sense of what's going to happen. Force doesn't actually give you a good sense of what's going to happen unless you know the object's mass. And that's going to come into play in a future slide. Anywho. F equals ma. Bread and butter skill. We're going to be using it the next 2 weeks. It's kind of like the equation. So there's really only like 2 more equations. You know what? Like, we're going to find that the force due to gravity is m times g. I'm just going to foreshadow that for you all. A is g. Wow. Like, that'll show up in a future slide. That's another equation. And then we'll learn the friction one. And that's it. That's the only last equations to teach you all before this upcoming test. So that's, I'm like, we're basically, and they basically all come down to this. So, okay. So just to test this understanding of variables, Elon Musk's Roadster on Earth was about 1,250 kilograms. If you all didn't know, he strapped it to the top of a rocket, and it's in space now. There's a website for it. You can look up where his Roadster is in space. It's orbiting things. Great. So his Roadster on Earth was about 1,250 kilograms. What is its mass now that it's in space? Is its mass 1,250 times 9.8 newtons? Is its mass 1,250 newtons? Is its mass 1,250 kilograms? Or is its mass 0 newtons? All right, 20 more seconds. We'll close it out in 5, 4, 3, 2, 1. So really, this is just testing if you realize kilograms is the unit for mass. It has the same mass in space. Mass is not weight. That's the major thing that you don't want to mix up. So mass is not weight. The amount of stuff that something has is its mass. That doesn't change no matter where you go. Mars, Jupiter, space, Earth, whatever. The mass of this baseball is going to be the same as long as I don't cut off a chunk of this baseball or add a chunk to it. The only way you change mass is you add stuff to it or you take away stuff from it. Weight is a different thing entirely. So weight, mass is how much stuff something is made of. The units are kilograms. Weight is the force due to gravity. The units are newtons, and we'll see another slide of this in the next slideshow. We'll actually calculate things with it. But weight is mass times acceleration. It's mass times gravity, because acceleration due to gravity. G is the acceleration. That's all we did here. Is we said, hey, I got an object. It's on Earth. It's experiencing a force. What's the value of acceleration that gravity causes? 9.8. So you just take the mass and you multiply it by 9.8, and ta-da, you have figured out the force. Just to give you all a good kind of touchstone, because like how much is 1 Newton? So this baseball, a baseball has a mass of 0.5 kilograms roughly. This is going to be a weird thing. So on Earth, 1 kilogram equals 2.2 pounds. On Earth. I know I'm doing mass to weight, but it's weird. On Earth, 1 kilogram is 2.2 pounds. G is 9.8. So if you want to find the force due to gravity, it's just 0.5 times 9.8. And the long and short of this is that a baseball has a weight of 4.9 newtons, about 5 newtons. So if you are holding a baseball in your hand, that's about 5 newtons. If you're holding like a remote control, that's about like 1 newton. Remote controls are generally pretty light. So that just gives you a touch point of like how much is a newton. If you came into this class knowing how much a newton is, you kind of have a better sense of it than I do. I actually have to like do these kind of things to figure that out. Like even though I've done physics, I just haven't stopped that much and thought about it. But yeah, a remote control, when you hold that, how much it pushes your hand is about 1 newton. And yeah, a kilogram on Earth is equal to 2.2 pounds. That's another kind of useful thing. Don't need to know it, but it's nice. And I just assumed my baseball was like a pound on Earth. All right. Okay. This type of problem. I have not given you all these types of problems. This is going to be the first time we see this. This is a problem where I have 2 objects and I say they're different. How is this third variable affected by these differences? And this is something we're going to do quite a bit of in this class. So this is our first case of this. Object A has half the mass of object B. I want to accelerate object A 4 times as much as object B. To do so, how does the force of A going to compare to the force of B? If I want to accelerate object A 4 times as much, how much harder or weaker do I need to push object A to make that happen? Do I need to, I push them the same and life is good? Is it that I push object A twice as much as object B? I push it with 2 times the force? Is it that I push object A with 4 times the force to achieve that result? Or is it that I push object A with half as much force as object B? See if y'all can come up with the answer, and then I will show you there's a mathematical technique for doing this that's nice and straightforward. You can kind of do this somewhat in your head if you think about it, but I'm going to show you all after this. I'll even leave the question open so you can change your answer and all that jazz. But for now, just give it a try. And then in like a minute, I'll start walking through how you can do these types of problems. All right, so again, I'm going to leave it open so you can still answer it, change your answer, all that good stuff. So the way we're going to solve this is actually the way we solve kind of all our problems. We're going to write down our givens. So object A has half the mass of object B. So that means the mass of A is half the mass of B. If the mass of B is 2, the mass of A is 1. If the mass of B is 4, the mass of A is 2. You can see if you put in numbers there that works out. One of the things sometimes people can accidentally do is they can accidentally maybe put that it's this. This would say that the mass of A is 2 times as big. Make up numbers. If the mass of B is 2, 2 times 2 is 4. That's the wrong direction. So you can always make up numbers to check your work. It's half. So we check a half here. Fantastic. I want the acceleration of A to be 4 times the acceleration of B. So I want the acceleration of A to be 4 times the acceleration of B. Just writing out in math what is written in words. My question is, how does the force of A compare to the force of B? Is it half as big, 2 times as big? What number should go in front there? How much bigger or smaller is it? So to do this, we need to find the relationship between force and the variables that changed. What is the relationship between force, mass, and acceleration? F equals ma. And so this expression shows us that as mass goes up, if my mass goes up, it's going to make my force go up. If my acceleration goes up, it's going to make my force go up. These problems are kind of an exercise in seeing, do the equations make sense? If something increases, how does it affect something else? If something decreases, how does it affect something else? And all doing it in terms of variables as opposed to putting in numbers. And I think this is a useful exercise for just kind of seeing as this changes, how is something else changed? So how do we do this? We write FA equals MA times AA. You know, mass times acceleration. Mass of A times acceleration of A equals the force of A. All A's. Great. But I want it in terms of B. So what do? I swap these out in terms of B. So I'm going to swap them out with my givens. I'm going to swap the mass of A. I'm going to put it in terms of the mass of B. I'm going to swap the acceleration of A with the acceleration of B. What's the point of this? We're going to pull all those numbers to the front, all the changes. So we're going to pull that 1/2 to the front. So force of A is going to equal 1/2 times 4 times the mass of B times the acceleration of B. And then the punchline here, the final thing that helps us make sense of this all, is what is the force of B? Well, it's the mass of B times the acceleration of B. Oh, look, we have the mass of B and the acceleration of B. That is the force of B. So we can swap that in. That's the reason we did this. We put it all in terms of the other's variables. We pull all the numbers to the front. And long story short, you get 1/2 of 4 is 2. 2 times the force of B. And there you go. So this shows us that if the mass is half, that should have made my force go down, but the acceleration was 4 times as much, so that made it go up, and they kind of cancel each other out. And my final result is that my force of A is 2 times my force of B. And that's how we do this. So give you a few seconds if you haven't changed your answer, whatever, to this one. Again, you get most of the points just for answering, but since I haven't showed you all how to do this, it has enough steps. I worked through it before I close it. In 3, 2, 1. I don't want to leave it open forever because I'll forget to close it, and then who knows what happens. Great. So this is going to be a really common theme in this class where I'm going to give you an equation, and I'm going to say, what happens to a variable when I change these other variables? And so it's practicing working with these equations. And this is just a useful skill. What happens to this if these other things change? So I always kind of think of this more in engineering terms because I think it's easier to explain. But the same is true of medical. It's like if you had a beam, a structural beam made of concrete. How much stronger would that beam be if I made it twice the radius? And you'd have to, and like coming up with something on the fly without having to do a bunch of crazy math with actual numbers and all that jazz, it's useful. So here's another example. Object A experiences 4 times the force of object B, and object A has 3 times the mass of object B. How does the acceleration of A compare to B? So I'll work through this one as well just to give us some extra practice because I do love these so much, and I want to give us make certain I prepare you all. And they're not going to show up in the problem sets, but they will show up on quizzes and tests and things like. So these kind of questions are conceptual questions. You do not need a calculator for this. I mean, it was a half times 4, like that was the level of complexity of math. So anywho, object A has 4 times the force of object B. Object A has 3 times the mass of object B. And my question is, how does the acceleration of A compare to the acceleration of B? So this one's actually more interesting because it says, hey, I have a different force and I have a different mass. How is my object going to accelerate differently? Is it going to accelerate more or less? As these things vary. So we are going to still use the relationship between force, mass, and acceleration is F equals ma. However, before we start putting in stuff to make our life a little easier, we care about A, so we're going to rearrange this equation for A. You want to rearrange it for the variable you care about, which in this case is A. So A equals F over m. More force, more acceleration. More mass, less acceleration. That's what this equation tells us. Force being on the top means as that goes up, acceleration goes up. Mass being on the bottom means as mass goes up, the acceleration goes down. Again, the equations mean something. And these problems help us to kind of get a sense of what they mean. So same exact process as the last one. We're just going to write the acceleration of A is FA over MA, all in A's, and then we swap them out. So AA is going to equal 4 times the force of B divided by 3 times the mass of B. Just swapped them in. I took this one and I put it there. I took the mass and I put it on the bottom. Just making the swaps, putting it in terms of the other variables. And then you pull those out. So the acceleration of A is going to be 4/3 the force of B over the mass of B. And then you're like, again, what's up with that? Remember, force over mass is acceleration. So, long story short, the acceleration of A is 4/3 the acceleration of B. And there you go. You didn't have to do a bunch of mental gymnastics. You didn't have to think about as force goes up, what happens? As mass goes up, what happens? we can see that here. As force goes up, my acceleration went up by 4 times. My mass was 3 times bigger, so that made it 3 times smaller because it was on the bottom. So you get to see all that as the final thing. And if you're like, man, I want more practice of these, or like, I didn't quite understand that, and there's only 2 examples here, I want to point out to y'all that ChatGPT is a fantastic resource for making additional problems. Anytime you all have a problem that you want more practice of, and this is true of probably any of your classes nowadays, using AI is a fantastic tool for studying. AI is like the new Googling. Back in the day, 5, 10 years ago, if you want to learn something, you want additional practice, how do you find it? You Google it. And you can still do that. Tons of resources exist out there. AI is effectively, it's read all of those various resources, and to that end, it can generate really specific things for you. I like to think of, when I use ChatGPT, it's almost like having a chat window with someone that knows the material really well. It doesn't mean they're going to do it perfectly. So always keep that in mind. AI is not perfect. If you all send me a bunch of emails, I will generally answer them pretty accurately, but maybe 1 in 100 I get wrong. AI is in a similar camp. If you message a bunch of, it will have things that aren't quite right. But one of the things you can do, so I just copy and paste the problem and I ask it, can you please, and this is also an interesting thing, you don't need to be nice to it. But I still do the nice things because it keeps me in a good practice of just being courteous in my writing. Because at some point, if you're not, and then whatever, it just gets you in good practice. AI doesn't care if you're nice, but it just keeps you in a good practice of when you write emails to people being kind. Can you please make several different versions of this problem? And you can even say, maybe make it instead of the acceleration changing, I want to force or whatever. And one, it just goes through and solves the problem. Oh, no, actually, last time, it's interesting. It generates different ones. When I asked this exact, pretty much similar prompt, it solved the problem first. This one, it just automatically generated these. Yeah, and so it's nice. Now, all of these are, how does the acceleration compare? How does the acceleration compare? How does the acceleration compare? If you're like, what if the problem instead was asking how mass would be affected? Whatever. You're like, I want to rearrange the situation. You can ask it these questions. Object A, look, there you go. Object A, X experiences 4 times the acceleration under the same force. How does the mass compare? Yada, yada. This is a tool, and it's a tool nowadays that you do not have to learn how to use this tool. But in my opinion, it makes your life more efficient. It's kind of like the difference between, again, this is my perspective on this. Time will tell whether or not I'm correct. I kind of view this like, again, when Google came out and people said, I don't need Google, I'll just go to the library and find books on it. That still works, but it's less efficient. By using this, in my opinion, you get more than what I've currently found Googling stuff does, and you can ask follow-up questions and all that good stuff. So anyway, use it. Take advantage of it. I genuinely believe that people that learn how to use this will be more efficient workers and therefore more marketable workers. So test it for yourself. Time will tell whether or not I'm correct. Okay. I do want to try to get to Newton's third law. My question is, okay, we're going to skip this one. I'm going to solve this problem, and we'll do Newton's third law on Thursday. So let me solve this problem. This problem is a kinematics problem and a force problem. We're going to see that. That's going to be a really common trend where kinematics and force problems go together. Because remember, kinematics is describing the motion. Force is saying why is there a motion. So they're both about motion. All right, 80 kilogram passenger and an SUV is traveling at 1 times 10 to the 2, 100 kilometers per hour. And they're wearing a seatbelt. Yay! The driver slams on the brakes and the SUV stops in 45 meters. Find the force of the seatbelt on the passenger. Go ahead, y'all, write down the givens. Go through the process. The same way that we've been solving problems, we're still going to do that. What's given? What are we solving for? Step 3, what equation? Try it out. I'll give you all a few moments. All right, so there is 4 givens in this problem. Our mass is 80 kilograms. Our velocity is 1 times 10 to the 2. That's 100 kilometers per hour. Is that my initial or my final? Initial. Anytime you all are working with velocities, you always should ask yourself that question. That should be a default. Whenever you see velocity, you need to ask yourself, is it initial or is it final? And then you got to convert the units. Do that sooner than later. If you don't do it now, you might forget. That's just worked for me in life. So we're going to convert it to meters by multiplying by 10 to the 3, multiplying by 1,000. We're going to convert to seconds by dividing by 60 times 60, which will be 3,600. So I'm converting from kilometers per hour to meters per second. In case you're like, what happened here? I'll just make it maybe a little bit more explicit. And then calculate. It comes out to like 27 or something like that. Again, I did not do that in my head. Whenever you all hear me say like a number, that's because I taught this class this morning and I did it this morning. I cannot do this in my head. It's a silly exercise to even try to do so. I don't know. Some people's brains might be able to do it, but not mine. 27.78 meters per second. And the last thing we know is delta x. It's 45 meters. My change in location, my displacement. You could have called the initial position 0 and the final position 45. Same thing. All right, we're solving for force. There is literally only a single equation I've given you with force in it. There is only one option, which basically means it's not an option, like it's going to be the thing you're going to use. F equals ma. And so when you're solving these problems, this is why going through these steps will help you realize things that might not immediately seem obvious. So for example here, look, this is the only equation we have for force, F equals ma. Immediately when we look at this, I know mass, I don't know acceleration. So that immediately then makes you think, how do I find acceleration? I need it. I have literally no other options. How do I find acceleration? We only have a few skills at this point. Kinematics is our only option. Like, that's the only thing I've really taught y'all. So you look at the kinematics equations. What do you have? What do you need? Oh, there is another given I forgot to put here. What is it? Final velocity equals 0. It's going to stop. I mean, it says so. So, if you're like, man, what if I forget these givens? When you're looking at kinematics equations, just ask yourself, do I know, if you're like, man, I don't feel like I don't have enough information. Ask yourself, do I know the acceleration? You look through the problem. No, I have no idea. Do I know the time? No, I don't know. Do I know the final velocity? Oh, I missed the word stops. I do know the final velocity. So you're going to use VF squared equals V naught squared plus 2A delta X. That's an option. If you want, you could find the time and then use a different equation. All of it works, but this is the one that immediately works. And you just plug in the numbers. So 0 squared equals 27.78 squared plus 2 times the acceleration, because we need acceleration, remember, to find the force, times 45. You move things around. 27.78 squared is going to be 771. We're going to subtract that to the other side. For the sake of space, I'm doing 2 algebra steps in one go. Ooh, 3 algebra steps. I squared it. I subtracted it over. And then the acceleration is going to be negative 771.728 divided by 90. And we're going to get an acceleration of 8.57. Pretty reasonable acceleration. It's about a little bit less than 1g. 1g is a lot more than you might think it is. So that's kind of a fun fact. Also, another fun fact for you, the Cybertruck can accelerate with 1g. There you go. That's the amount of acceleration. We did the math on it. 0 to 60 in like 2 seconds, 2 point something seconds. It comes out to 1g of acceleration, which is just kind of a fun number. I only know this because my neighbor got a Cybertruck. It's very easy to find my house now. Yeah, he took me on a ride. It was very interesting. Great turning radius, too. The back wheels rotate. It's very interesting. Anywho, great. We got the acceleration. It's pretty decent. Then we just multiply it by the mass, and we're done. And yeah, so this is a problem where we can see the connection between kinematics and that. And this is something that will pop up. It's really easy. Find the acceleration, then find the force, or find the acceleration, then do some kinematics, vice versa. And we get a final force of negative 685.6. Negative, what does negative mean? This is the last kind of check and we'll be done. What is a negative vector? If this is in the horizontal direction, what does the negative mean in the left-right direction? That means you're going to the left. And we assume this car was going to the right. The force was to the left. That's why it slowed down. It all works. So there you go, y'all. Intro to forces. We'll finish up Newton's third law and then get into drawing pictures and things. It's fun stuff. Look at the world around you. Think of all the forces. They're everywhere. Every single push or pull. Every single interaction is a force.